Welcome to qnawire.
In this problem, we're going to talk about angular momentum and torque. So first, remember that the angular momentum L associated with a rotating particle is equal to the mass of the particle times the radius of rotation times the linear the linear speed v. Also, remember that the torque is equal to the change in angular momentum divided by the change in time. So it's delta L divided by delta T. And finally, what we're going to need to our exercise is that the work exerted can be calculated as the torque exerted over a particle times the variation in the angular position of that particle. So now we can go on to our problem. We have a water wheel that has a radius of 3 meters, and we have water that enters the water wheel with an initial speed of, of 7 meters per second and exits the water wheel with a final speed of 3.8 meters per second. And in question A, we have to consider that the flux of water through the water wheel is 85 kilograms per second. And we have to calculate um, at what rate, what is the rate with which the water delivers angular momentum to the water wheel. So the water loses angular momentum, and this angular momentum ends up with the water wheel. Okay, so let's calculate what is the loss in angular momentum of the water. Notice that the initial angular momentum is the mass of the water. This actually is the mass divided by time. So this is the mass of the water times the radius of the water wheel times the initial velocity, while the final one is the mass times the radius times the final velocity. So the change in angular momentum is mr times vf minus vi. Okay, so this is 85 kilograms in 1 second. I'm going to calculate the change in angular momentum per unit time. So it's 85 kilograms per second times 3 meters times 7 minus 3.8, that is 3.2 meters per second. So delta L, delta T is equal to 816 kilograms meters squared per second per second. Okay, this is the answer. Then in question B, our goal is to calculate what is the torque over the water wheel. And actually, I'm sorry, there is a minus here. I forgot to write it. So the force, I'm sorry, the change in angular momentum is equal to to minus 816 kilograms meters squared per second squared. But we have to notice that this is the angular momentum lost by the water, meaning that the angular momentum gained by the water wheel has the same magnitude but a positive sign. So the negative sign vanishes, and we have just the positive sign here. So actually, I'm going to put a minus sign here just to calculate the change in angular momentum of the water wheel. I'm going to even write it as delta LW. Then we have to calculate the torque. Remember that the torque is just the change in the angular momentum of the water wheel times divided by the time. So it's exactly the same as before, as equation A, 816 kilograms meters squared per second per second. And then in question C, we have to notice that the water wheel takes a time of 5.5 seconds to complete one revolution. So the period is 5.5 seconds. And our goal is to calculate what is the power delivered by the wheel. So we're going to calculate the power. The power must be equal to the torque times delta theta. Remember that this is the energy delivered by the wheel, delivered to the wheel, I'm sorry, divided by the time that it takes for this energy to be delivered. And if delta theta is just 2 pi, one revolution, then the time is 5.5 seconds. So tau is 816 kilograms meters squared per second squared times 2 pi radians divided by 5.5 seconds. So the power is equal to 932 watts. And this is the answer to our exercise.